Welcome to today's Explainer. We are going to look right under the hood of machine learning. We hear the term artificial intelligence thrown around all the time, in the news, at work, on social media. But how often do you stop and wonder how it actually works on a fundamental level? Most of us just accept the results as a given. Well, today we are stripping away the magic and looking squarely at the mechanics.
Think about your daily routine for a second. You open your favorite Maps app, punch in the location for your go-to coffee shop, and the app immediately tells you it will take exactly 12 minutes. How does your phone know that? How does it instantly factor in things like the number of stop signs, the speed limits, and the distance, synthesizing all of that into one highly accurate prediction? To understand this, we are going to build a conceptual machine learning engine from scratch. It's not magic, it's math, and it all starts with a really foundational concept called linear regression. Here is our roadmap for today. First, what is linear regression? Second, measuring mistakes with loss. Third, the gradient descent journey. And finally, tuning machine learning hyperparameters. Let's dive in. Section 1. What is linear regression? Okay, let's demystify the core equation that makes prediction possible. If you want to predict a continuous number, like the exact amount of minutes on your commute or miles per gallon for a car, you need a reliable mathematical framework. And the beautiful thing here is that machine learning is literally just your old high school algebra wearing a slightly different outfit. Think back to the classic equation for a straight line. Now look at the machine learning equivalent. Let's map this out. The y from algebra becomes y prime, which is our predicted output. In our case, the predicted commute time. The x is our input feature, like the number of stop signs on our route. The m, representing the slope, becomes a w for weight. And the b, well, that remains a b, but we call it bias. Let's break those parameters down a bit further. Think of weight as a physical dial inside our engine that determines exactly how much time a single feature adds to your overall commute. Just like the slope in algebra, the weight multiplies our input feature. So let's say your route to the coffee shop has exactly 5 stop signs, and the machine calculates that a single stop sign adds 2 minutes to your trip. Well, then the weight for the stop sign feature is 2. 5 stop signs multiplied by a weight of 2 adds 10 minutes to the total commute. Makes sense, right? The bias, on the other hand, is our baseline starting point. It represents the absolute minimum time your commute would take, even if the route had 0 stop signs, just distance and normal speed alone. During training, the machine's entire job is to calculate the perfect weight and the perfect bias to make accurate predictions. But here's the catch. Initially, the machine doesn't know any better. It just guesses these values. It picks completely random numbers. And as we all know, wild guesses inevitably lead to mistakes. Section 2, measuring mistakes with loss. Which brings us to a super crucial concept. If our newly built engine wildly guesses and predicts a commute of 20 minutes, but you drive the route and it actually takes you 15 minutes, we need a mathematical way to measure that flaw. We absolutely can't fix what we can't measure. In machine learning, this measurement is called loss. The engine only cares about the physical distance of the mistake, stripping away any negative signs so it can focus purely on the magnitude of the error. Whether it guesses 20 and the answer is 15, or it guesses 10 and the answer is 15, the difference is exactly 5 minutes either way. The direction, being early or being late, just doesn't matter. The absolute distance of the mistake is the whole shebang. The fundamental goal of training a model is to minimize this loss. Now, what's really interesting here is that we have 2 competing mathematical tools to measure our engine's mistakes across the whole dataset: MAE and MSE. Mean absolute error, or MAE, simply takes the absolute difference of all predictions and averages them out. Mean squared error, or MSE, takes those differences and actually squares them before averaging. Why on earth would we square them? Well, squaring a large mistake makes it look absolutely massive to the machine. It's basically sounding a much louder alarm, forcing the machine to pay incredibly close attention to that one specific error. Deciding between the two depends entirely on your specific data. Let's say you're looking at a whole year of your daily commutes. What if there was a huge anomaly? Imagine a freak snowstorm or a local parade completely shut down your route one Tuesday, turning your standard 15-minute drive into a grueling 3-hour ordeal. If you use MSE, the engine will aggressively bend your model to chase that massive 3-hour outlier, because that squared error penalty is just screaming at it to fix the huge gap. MAE, on the other hand, will comfortably ignore that one crazy snowstorm, keeping your model focused on the realistic average of your normal daily driving. It really just comes down to a choice of how sensitive you want your engine to be to wild one-off events. Section 3, the gradient descent journey. Okay, So we've made a prediction, and we've successfully measured our mistake using a loss function. Now what? Once we know the loss, we need a mechanism to actually fix the engine. And this brings us to an elegant mathematical loop called gradient descent. This four-step loop is the exact pulse of how a machine iterates and genuinely learns from its mistakes. Step 1, it calculates the loss. Step 2, it uses calculus to find a downward slope, the direction that actually leads to a smaller mistake. Step 3, it takes a tiny step, tweaking the weight and bias slightly. And step 4, it repeats the process. It does this over and over, continuously tweaking the dials until the loss shrinks.
Visualizing this process makes it incredibly intuitive. Because linear models have this distinct convex shape, you can picture gradient descent exactly like dropping a ball into a large, smooth bowl and just watching it roll downhill. The high, steep sides of the bowl represent high loss, terrible, wildly inaccurate predictions. The very bottom of the bowl represents the lowest possible loss. At every single step of that loop we just discussed, the machine is really just trying to roll the ball a little further down the slope toward the center. And what happens when it finally reaches the bottom, when that rolling ball comes to a complete stop at the lowest possible loss? Our model has achieved a state called convergence. Our engine is fully optimized. The weight and the bias are now perfectly tuned to give you the absolute most accurate prediction possible for your morning commute to the coffee shop. The machine has learned. Section 4. Tuning machine learning hyperparameters. But wait a second. Who is controlling exactly how the machine goes about this rolling learning process? Before we run this engine, we, the builders, have to tune a few master dials on the dashboard. It's totally essential to understand this distinction. Parameters are the internal gears the machine fixes itself through trial and error. But hyperparameters? Those are the dashboard dials you control as the human engineer. You dictate the rules of the trial and error by setting the hyperparameters before you even press start. The most important hyperparameter you will tune is the learning rate. This controls the physical size of the small step the model takes during gradient descent. If your learning rate is too small, the ball takes forever to roll down the hill, inching along painfully, agonizingly slowly. But if it's too large, oh boy, the ball wildly bounces out of the bowl, flying from one high-loss side to the other, completely out of control and never actually converges at the bottom. Finding that perfect Goldilocks learning rate, not too big, not too small, is a massive part of a machine learning engineer's job. We also use the batch size dial to control how many data points the engine looks at before updating its internal gears. Imagine trying to learn from thousands of past commutes. If you look at every single commute in your history before adjusting your formula, that's a full batch. Highly precise, sure, but incredibly slow to compute. If you adjust your formula after looking at just one single random commute, that's stochastic gradient descent, super fast but very noisy and chaotic. The sweet spot in the industry is usually mini-batch, where you look at a manageable, practical chunk of data, choosing a really smart balance between slow precision and fast, noisy updates. Finally, we set the epochs. This tells our engine exactly how many times it needs to review the entire history of coffee shop commutes to achieve perfect convergence. One epoch means the machine has seen every single piece of data exactly once. Typically, a machine needs many epochs, multiple full passes over the dataset, to finally push that ball all the way to the very bottom of the convex loss bowl. And that is the true architecture of a machine learning engine. As we wrap up this explainer, I want you to consider how mastering these basic dials, loss, gradient descent, and hyperparameters is really the first foundational step toward unlocking the advanced artificial intelligence shaping our entire future. Because whether it's predicting a quick 5-minute drive to the local coffee shop or powering a massive large language model that is actively reading and processing millions upon millions of texts, the core heartbeat of the machine is exactly the same. It measures the mistake, it finds the slope, it rolls down the hill, and it converges. Thanks for joining me on this explainer. So the next time your Maps app predicts your exact arrival time, you'll know exactly what's happening under the hood, won't you?